Perfect. So yeah, today I'm gonna talk about the high-order A-Stable Deferred Correction method. So why work on time integration? Time integration is one of the key of unstudied problem in numerical approach. So most of the problem can be synthesized with a simple ODE equation like that. So our challenge is to integrate this ODE. We have different methods for that. We can use the Runge-Kuttar approximation or the BDF approximation, for example, but we want to develop a method that respects some criteria. For example, we want a high-order temporal method, but also A-stable method, very useful for that assure the stability for stiff equation. And so, for example, BDF equation, BDF discretization are A-stable for BDF1 and BDF2, but it's not A-stable. So that's why we want to develop a different correction to have high order and keep the A stability in the same time. And we also want to build a method that is suitable for time step adaptation. That means that we can use a non-constant time step in our simulation. So to work on our method, we're gonna use a very simple test case. So let's work with the parabolic evolution problem, such as the heat equation. And we're going to use the manufactured solution method to prove the good order of convergence. So here S will be defined by the injection of the exact solution in the heat equation. We're also going to use a norm to measure our error. So here, the norm is the L2 norm on the space domain. And after, we're going to use the maximum every time step to measure the maximum of error of our method. So about the domain, we're going to use a one-dimension domain with a very simple solution. This exact solution is simple, but in fact, it sheds light on every problem that we can have, because it also work with harder problem after. So here we have our domain with the initial condition, and we have our two boundary condition that depends on time. We'll see after that it matters. And also for the simulation, we're going to use P3 interpolant for the finite element calcul after. Note that it also works for every kind of interpolant. It's only simpler because like that, we don't have error due to the integration of X terms. So it's easier. After, it's also important to focus on the time step. We based our simulation on the procedure developed by because it showed that if our method is stable for constant time step like that, we also have to prove that it's still stable for when we change the time step. So this procedure has been developed to test the robustness of the method. It's also important to note that during the refinement of the variant time step like that, we're going to keep the ratio between K1 and K2. So K1 will always be 4 times bigger than K2. So now we have our context, our simple test case. Let's talk about the method. So deferred correction method is based on the BDF method. So BDF discretization for like a order n can be written like that, where we approximate the solution U bar with the sum with coefficient Ci like that. So first, with the first BDF discretization, we obtain a solution U bar, and we can use this solution to calculate the truncation error that we know D. And then we correct another BDF with this correction, but using the previous solution. So here we have a new method based on there is the basic of the BDF, but we correct with the previous solution. So like that, we can have a new solution U, but with an order n+1, we just win an order by correcting with the truncation error like that. So for the simple example, we can consider the Euler method, which is also the BDF1 method. So if we have the first BDF1, we can obtain the solution U hat here. With that, we can calculate the truncation error of this first method, then we're not here. So with this correction, we correct anew the Euler method, and it forms a new method of order 2. So now we have a new solution U bar that is of order 2, and we can make the same correction again. So we calculate a new truncation error based on the previous solution. So it's based on U bar, and we obtain a new another time a new solution U that is of the convergence is supposed to be order 3. So this method helps to keep because BDF1 is A-stable, as I said, it helps to build a method of order 3, but still A-stable, because if we build a BDF3, for example, it's order 3, of course, but it's not A-stable. But thanks to this method, we still have the A-stability for an order 3. And also you can note that we're doing 3 times the operation, so it's extra cost in the simulation. But it's important to see that because the methods are quite similar, we don't calculate the matrix another time. Like the matrix between different simulations are identical. So there is a price to pay to keep the stability, but it's not so high because the scheme are quite the same. So now if we simulate our test case, we can plot the error calculated by the norm that I presented before. And we can see that by refining the time step, the results are correct. If we plot the BDF1 error, we have an order of convergence of 1. If we plot the DC2 BDF1, so we have an order higher than 2, and it's the same thing for DC3 BDF1. So now we can also make the same method for a BDF2 method. So now we start from a BDF2 discretization. We still have our solution U bar, and then we calculate the truncation error here. And thanks to that, we build a new method to have a new solution U that is this time of order 3. Every time we gain an order. So about the result, we do the same thing with constant time step. If we plot the error, we have the good order of convergence for BDF2. It's a very well-known method, but also DC3 BDF2, where by correcting we can win an order. But then problem appears when we use variable time step. I told you before that it's very important to check with different time step. We saw that with constant time step it was working well, but now we can see that with the method DC3 BDF1, it's still working with the constant time step, no problem. But for the variable time step, we can see that there is an order reduction. So what is the cause of this order reduction? If we check on with the graph of error, we can see that this order reduction is due to peak of error on the boundary. So we know that the problem is linked with the boundary, and it also only appears when we use boundary condition depending on time. It doesn't appear when when the boundary condition doesn't depend on time. So we need to work on that. And to do that, we've used the Verve implementation, because before we were using the Dirichlet boundary condition to fix the solution U on the boundary. But now we're going to impose a differential equation on the boundary, introducing a new variable V, and that corresponds to the derivative of the exact solution gamma. And how do we implement this this new differential equation? Because we're working in finite element, we can directly implement this this differential equation in the weak formulation. So before we had, with Dirichlet condition, we had the strong boundary formulation where Dirichlet terms appear here, but it's null. But now we impose the new differential equation using the Lagrange multiplier. So we want to impose the value of U on the boundary equal to V there. So it's on the boundary, and we want that V correspond to the differential equation equal gamma dot. But then to impose this new value of U, we use the Lagrange multiplier here. So we have this new weak formulation that we can directly use in the code. So thanks to that, thanks to this new implementation, we can fix our problem of
1 minute.
Yeah, of convergence. Here we can see on these two curves that either if it's constant on variable, we still have the good, or we now have the good order of convergence. The problem is more than when we check on the secondary variable, which is the Lagrange multiplier, we have a loss of, we have a reduction order for variable time step. But we need to think about what does it represent. Because in fact, Lagrange multiplier in our situation could be, is considered as the heat flux. So we don't measure the L2 norm of the Lagrange multiplier. It makes sense to measure the integral. And like that, we can see that we have the good order of convergence. So this is our result for a simple test case, but now we're working with this method on Navier-Stokes equation and in 2 dimension, and it's currently a work in progress. So thank you if you have a question.
Thank you. We have 1 minute.